In this tutorial, we're going to talk about descriptive spatial statistics. We're going to define the spatial mean, the standard deviational ellipse, and the standard distance, and then talk about how each of those three are used with some examples from studies focused on disease ecology and public health. In this tutorial, we're going to use data from a study by Blackburn and others, published in 2014 in the Annals of the Association of American Geographers. In this tutorial, what we'll be exploring are the descriptive spatial statistics that describe the data associated with these individual points contained inside of this individual polygon. At each individual point location, an individual fly trap was set up for an approximate 24-hour period. Biting flies would be attracted to the blue and black, fly into the trap, crawl up into the catch bottles, and then ultimately expire and be caught inside of a catch bag. And these traps were set up at each of the individual sites that you can see on screen. At each individual location, we calculated the catch per unit effort, or the CPUE, of the number of flies caught per sampling period. So it's the number of flies caught per hour across those trap sites. One of the first things we notice when we look at a graduated symbology of those individual trap sites is that some traps collected a much higher number of flies than other sites. In this tutorial, we're going to use the calculation of the spatial mean, standard deviational ellipses, and the standard distance to ask two questions. The first question is focused on, are the trap locations representative of the ranch? So we want to ask questions about the point distribution itself, or questions about the XY locations of trap sites. Our second set of questions is going to pertain to the catch per unit effort values. Those are these values that we talked about a moment ago. And we want to ask, are flies concentrated at trap sites? So we have a question focused first on the distribution of traps, and a second set of questions using those statistics focused on the CPUE values, or the attributes. As you're watching this video and thinking about your own data, this second example could be focused on any attribute value that describes differences in quantities at different site locations. Let's first talk about what we refer to as either the spatial mean or the mean center. And of course, if you're using QGIS, it'll be spelled differently. To calculate the mean center of the individual points, or the black dots that we saw in the last slide, we can calculate the mean center as simply the summation of all the X locations divided by the number of points, and then repeat the same thing for the number of Y locations. So following this nomenclature or notation, which comes from the desktop.arcgis website, we have three things that we need to keep track of. We need to keep track of the X locations, the Y of the locations, and the number of individual locations. And here, I simply denotes which file we're working with. So on the previous map, those were the black dots. This calculation would result in one point file with one location. And that would represent the spatial mean of the sample sites. We can also calculate what we call the weighted mean center. And what we mean here is that we're going to weight the mean center by an attribute or some quantity, which in this case is going to be the CPUE, or the red dots. So the locations are the same, but now those individual locations will be weighted by that catch per unit effort value. So we're going to shift the position of the mean center toward where more flies were collected. To calculate the weighted mean center, following again on the notation from Esri, here we see again we have X and Y, and this time we're going to be multiplying those each by the weight, which in this case would be the CPUE value at each location or site. Then we're going to divide that by the sum of the weights. Again, I denoting whichever file we're working from. So again here, trap sites, and again the weights, the CPUE. Now let's talk about ways to measure dispersion around the mean. So we're interested in what the mean location is to get a sense of where the average point across that point distribution is. When we weight that mean, we're interested in whether or not that mean shifts geographically in one direction or another based on something like catch per unit effort. We're also interested in dispersion, or are we concentrated around that mean, or are we dispersed or spread out around the mean? And we're going to look at two measures of this. The first, standard deviational ellipses, give us both dispersion but also some measure of directionality around the mean. So not only are the points concentrated or dispersed, but also is there directionality to that. So following on with the notation from Esri and the notations from our last slide, to calculate the standard deviation ellipses, we need to know first the mean center. So we want to know how our data are distributed around that. So this time, x sub I minus x bar and y sub I minus yi are going to be the distances between the points. So the point location and the mean center. There's also going to be a calculation of the angle of rotation, which is how we're going to measure that overall directionality, or how we're going to pivot that ellipse to capture whether or not our data have a more north, south, east, or west distribution. Then we'll also get the deviations for the x and y axis to give us a sense of how tall and or how elongated that ellipse should be around the mean. So we'll know something about both dispersion and directionality from this set of calculations called the standard deviational ellipse. And for the final calculations in this tutorial, let's talk about the standard distance. The standard distance is going to give us a single value which is going to be our measure of dispersion. And when we create a polygon file, while the standard deviational calculations give us an ellipse, this is going to give us a circle, and the radius is going to be equal to the standard distance. So we're going to get a circle with a radius equal to the standard distance, where the center of that circle is going to be the spatial or the mean center. Following the notation on the Esri website and what we talked about a moment ago, here we still have the calculation of the distance from the point to the spatial or mean center. And so what we can see here is we're going to perform this calculation for x, perform this calculation for y, summate those into two values, which will equate to the standard distance in map units. We can also weight this. So again here, we see that we'll need a weighted mean center. We'll need the weight value, which for this example is the CPUE. And again, we'll see we're going to summate those weights in our denominator. And again, we can see we're going to tally this for each x and y into a single value in map units. So now that we've seen each of the three calculations and given examples of how these equations fit in the pieces of our individual file, our point file, let's go look at some examples. So let's first look at the example of the unweighted mean center. So notice here in the black dots we have our trap locations, and we've calculated the mean center here only for the XY locations. So all we're interested in here, because these data were projected, we're interested in the UTM locations of the trap sites, and we're asking whether or not this spatial mean is approximately in the center of the ranch, or is it shifted in a particular direction. And so we can see here that the mean is approximately in the center of the ranch. And we can see we've got a first standard deviation ellipse plotted here, and we can see that covers the approximate geography of the ranch with sort of a southwest to northeast distribution to it. Now let's look at that spatial mean and those standard deviation ellipses for the catch per unit effort data. And in this particular study, we subdivided the trapping events into 4 individual periods. So we have now 4 different colors that we're keeping track of. And what we can see over the course of this season is that we saw both a shift in directionality and we saw a shift in the mean center. So rather than having the mean center approximately here, which is what we saw for our unweighted, when we weighted, we saw that across the whole sampling interval, we saw this northeasterly shift in the spatial mean, and we saw some variation in that mean across the 4 sampling events. If we look at the directionality of the ellipses, we can see that during this time period indicated in orange, we had a much more even dispersion with an ellipse that was almost as tall as it is wide as compared to some of the other sampling periods, like this one denoted in red. And we can see a more west to east distribution in flycatches during the orange period. So they were concentrated here, the furthest north and east mean of the 4 periods, and fairly widely distributed around those locations. Whereas in our others, we had that more southwest to northeast that we saw here, but again, shifted more around that spatial mean. Now let's look at the standard distance values. And we can see the same story, the same information being provided here, and that our spatial means weighted are the same as they were in the last figure. But notice now we're just displaying standard distance as a circle. So we can't see any change in directionality, but we can see a reduction in the overall size of the standard distance circle in this time period compared to this time period. So the standard distance gives us a circle, and we can see that the dispersion was more concentrated in this setup 4 than in one of the other setups. So we still get information about dispersion when we weight these, but we don't get directionality that we saw in the ellipses. So with these metrics, using the unweighted mean, we saw that the trap locations were representative of the ranch with a mean center in the center geographically of the ranch, and not concentrated to one side of the ranch or the other. When we weighted those means, we saw a shift to the north and to the east, and when we looked at the dispersion around that mean with each the ellipses and the standard distance circles, we saw a more tight concentration and a more northerly concentration with each the ellipses and the standard distances than with those unweighted values. So those shifts in the weighted values are because of those high fly catch rates and not because of our sampling distribution around the ranch. So that's an example of why we would use both the weighted and unweighted values in a single study. Again, those weighted values telling us, are our sample sites evenly distributed or representative of the landscape? And here are our CPUE values concentrated in one part of the ranch versus some other part of the ranch. So there's a brief introduction and overview of the spatial descriptive statistics and at least one set of examples of how they're used. As a last example, let's look at how we use standard distance to set some parameters for another analysis performed in the same study. So here you can see again in the black dots our individual trap locations. And here in the background, this gray, light gray to dark gray increasing to red is the kernel density estimation of those catch per unit effort values. You can see our videos on the Sear Lab YouTube page about kernel density and how to build a heat map in another video. So we turn this into a continuous surface so we can map biting fly density across the ranch, and you can see that we have a concentration or a hotspot of flies here. So how did we set the parameters for the kernel density estimation? That's what standard distance helps with. So let's look at one of the parameters required for a kernel density estimation. So one parameter required is a grid cell size, because we're going to convert this discrete point distribution into a continuous surface. So we have to have some kind of a setting for choosing that. The second thing we have to choose is the bandwidth, or the radius that we're going to set around each trap location to calculate that smoothed kernel density estimate value. And that bandwidth setting can take many forms. One of those forms is what's defined as HOPT, or the optimal bandwidth, and that requires two pieces of information. First, it requires the sample size. That would come from the individual trap locations. We also need to know sigma, which is the standard distance in map units. So this calculation, 2 divided by 3n raised to the 1/4 power multiplied by the standard distance will give us a distance in map units to set our bandwidth to perform a kernel density estimation. So there we've seen an additional use for the standard distance, which is to set the parameters for some other spatial analysis. So as a brief summary, we've talked about descriptive, spatial statistics that we see frequently used and calculated with GIS software. We talked about the mean center. The mean center is going to be the mean X, mean Y location of a point file. We've talked about the standard deviation ellipses, which are giving us a measure of dispersion of points around the mean, spatial mean, and of directionality of that dispersion around the mean. And third, we've talked about the standard distance, which is a single measure of dispersion around the spatial mean. And it can also be used to help populate the kernel density bandwidth. As an additional note, we talked about each of these being performed as weighted and unweighted. And when they're weighted, in this case, we use the example of CPUE, but this could be any continuous attribute that you're interested in. So those metrics are useful for each helping to understand the spatial distribution of a data set that we're just starting to explore, and also possibly setting up parameters for other future analyses. I hope this is helpful. Good luck in your analyses.